great to be here, at least doing some mathematics. So I'm going to talk about collision times of random walks. And so I'll mainly focus on this part because I want to this be a very elementary kind of application of things. And in the end, I will quickly go to the sort of its application, how we came to it, uh, the application to the convergence and Brownian wave. And it's kind of sort of a very robust technique for showing one of the things about Brownian wave. And hopefully I can go to that end. And there are sort of similar things can be done in continuous time. I'm going to only concentrate on discrete time. In if time permits, which I doubt, I will just tell about what the continuous time results. Okay, so without further ado, let's start. So the co-authors for this work, of course, you all, probably many of you know Kumajit and David. I don't know whether David has joined us. If he has joined, hi David, and Chi Tran from. So they were in Lille now. David is back in Lille. Chi is still not. Okay, so uh, so let me go to the main plan of these talks. So collision time of random walks, that is the main topic that I'm going to sort of spend most of my time. And so I'll quickly now go through then quickly, if time permits, sort of as much as time things. Uh, Directed random tree models and Brownian web. We'll just discuss it. This is going to be very quick. And finally, if we can sort of come to the end for collision times, the application of collision times. Okay, so without, we can start. So, so collision time of random walks. So I will be, this will be very elementary to start with. So most of you, all of you know what's a random walk is. Let's still go over this. So I start with at a point A in the integer lattice. So A can be positive, negative, whatever. And I associate the increments from, so I'm just increments here. I'm taking +1 and -1. So you toss a coin. If you get head, you go from A to A+1 and A to A-1. And you continue doing this. And here I am putting A in the suffix because this is collision time of random walks. So there would be many random walks, at least 3. So for each of them, they will have independent increments. So to distinguish between different random walks, I have sort of put this A together. Okay, so let's just the elementary definition. I start at A, and how do I move from at time n? I just sum up the increments and I go to Sn plus A. S not plus, S not A plus the sum. And just quickly look at this. So if I start from 0, 0, the first coin toss, it's here a picture of this, it goes head. So you go up one step and then you go down one step, it's a tail, another tail, you go down one more step, you go up one more step, head, tail, head, head, and so on. So and then we just, as I said, we just join by line segments. So these are all very elementary. We do it in the first year of undergraduate, or maybe slightly later. But so now, so so we're going to focus on the entrance time or the heating time. So I'm going to take A to be non-zero, and we are looking at the first time from the non-zero A. You start the random walk at A, and when first time you hit 0. Okay, so this is the entrance time to 0. Okay, to the origin, as you said. And known results, we have all done this. This is essentially nothing but the reflection principle. Reflection principle will say that tau bigger than equal to n, the tail time, how much time it takes. So this is one of the things is that this is happens finitely in finite time, and the tail behaves like a power, and it is n to the power minus half, n to the power minus half, right? So where this is, of course, that is, this essentially means root n times this converges to a constant. And a, I have kept it here because of this. A is fixed, but so for this behavior, if you start at a, this is like constant times a. If you start at let's say a plus 2, then that the same constant times a plus 2 it would happen. Okay, so it behaves like this. Now let's talk about two random walks. Okay, so I start from two random walks. Now Sn 2i and 0. I take this 2i and 0, and I want them to look at the coalescing time. The first time they hit each other. Okay, uh, so they hit each other. That is probably should have said hitting time, but the coalescing time is I have used. I don't know why. Anyway, why I have taken 2i, because if they are of different parity, it is not even. This is even. Then they will not hit each other. They will cross each other without hitting, without being at a single point, right? So if it is, let's say, at 1 and this is 0, so they when this takes minus 1, so it would go to 0, and when this takes it has to take plus 1 or minus 1, it takes minus 1, and it goes to sort of it goes to plus 1, it goes to 1. So they cross each other but don't hit, and they will never hit. The parities would be always be different. Okay, so now with coalescing time, tau, it is tau of written. It is the first time this two meet. And so you take these two random walks, Sn2i and Sn0, take the difference. Now the random walk here will have a different increments. The increments would now be -2, 0, and 2. And the probabilities is easy to see that it is 1 by 4, half, and 1 by 4. Okay. And again, the same logic essentially applies to show that the coalescing time tail would behave like a constant times, again the starting distance here is 2i, so since I have not said I to be plus 1 minus 1, it would be sort of okay. Here also I should have said this is the absolute value. I somehow missed that. In the first day it should have been the absolute value of a. It's not a can be negative, so in that case it should be c times absolute value. So here also this is c1 times absolute value of 2i times 10. This c1 is essentially would be of like 2 times the c in this case. It is to do with the variance of the random walk. We will not get into this business, how these things, this is related with the what is known as the local limit theorem, but I'm not going into those business. Okay, now we want to talk about 3 random walks. Okay, and before that I want to do a very quick setup of something called martingales, and this would be elementary, so those who know it, it is would be very elementary for them. And but there are, I think there are many students, and so I want to sort of give them some sense what is going on. So I'll just quickly set up these things, and these are sort of elementary things. If they're if you're second year, you will be studying very soon, but it's a starting point. So we require 2 things. One is called a filtration. So what's the filtration? Filtration is a sequence of sigma algebras, and they should be non-decreasing, so are increasing in other sense. So sigma algebras are a collection of sets. So non-decreasing means that a set sort of fn's are non-decreasing. So fn and is would be contained in fn plus 1. So that is the thing. So it's as a set, the collection of set becomes bigger. And what is this, as all of you know? So this is essentially n plus 1 random variables. So this is set of all those sets, all set of all things which can be written as S naught to Sn. This belongs to some Hn, Hn plus 1. This is n plus 1 dimensional set. So all kinds of sets which can be written in that form. Okay. Now, of course, why this is increasing? That is clearly because if you have n plus 1, so the n plus 1th set you can think of H, which is in n plus 1 dimension, cross R. So that would mean that the set Fn, any set in Fn, would be S naught up to Sn in H, which is S1 up to Sn plus 1 in H cross R. So that is essentially the argument why it is increasing. Okay, next thing that you require is what is called a sequence of random variables, and you require three conditions. The first condition is that expectation of the absolute value is finite, and of course the second condition is xn is fn measurable, this fn measurable. And the third condition, so these two conditions are generally very trivial. Always you, without doing any work, also essentially you would find them. The third is the main condition. So, so Fn is should be thought of what is the accumulated knowledge up to that time, up to time n. So if you sort of say, tell me what is S naught up to, for example, look at this example, S naught up to Sn. So if I know that, what is the conditional expectation of the next step? So if the next step, so if you, the next step, it is the same as what happened as the nth step, then we call it martingale. And this definition is essentially in a formal way of saying xn plus 1 indicator A. So this is the definition, formal definition. Xn plus 1 indicator A is same as the expectation of that is same as expectation of xn indicator A. So for all A in the set Fn. Okay. This may seem very strange, but the definition that you know for discrete cases, think of the x1, x2, xn, they are discrete, uh, exactly the same. Same example, if you take the discrete, whatever the expectation this is, it matches exactly the same. Okay, so there is no, so think of in all our cases, these are all discrete. We are going to consider only discrete. So that definition holds. So you just take into that definition. Okay, so this is the main, one of the main things that I will keep want you to remember. So if I take A equal to omega, so this becomes 1 always. So this becomes xn, expectation of xn plus 1, which is equal to expectation of xn. So this is martingale, that this thing happens, that for every n, expectation of xn is same as expectation of x naught. This is a sort of thing that this is what would be, we will be using this. And let's quickly see an example. So if you see Sn, the Sn is this, sorry. So Sn is this, the random walk that we are talking about. Okay. So n plus 1th step. So if I know up to n plus 1th step, what would be the, if I know up to the nth step condition, what would be the value of n plus 1th step? So it would be whatever the value was at time n plus 1 with probability half, and minus that minus 1 with probability half, right? So if you take compute then the expectation, so it is just, then it becomes the value at time n. And you can do the same calculation, for example, for this process. It is just elementary calculation, write down the probabilities. This is expectation. So if I have to, these two are trivial, right? This mod of Sn plus mod of Sn is less than equal to mod A plus n. At time n, you can move at most n steps from A, and of course then therefore it is less than equal to A, and by definition it is measurable. it is measurable by, you are saying Fn to be the smallest sigma algebra with respect to which all of them are measurable. So therefore Sn is measurable. So these are trivial, these two things, as I said, is always become going to be trivial. Uh, the only thing that is this condition that you have to take care. And in this case, this you just, as I said, Sn plus 1 is going to be Sn plus 1 with probability half and Sn minus 1 with probability half. If up to Sn everything is fixed, so then you have, if you take expectation of that, so you can just get back Sn. Okay, so the next condition, next thing that you require is what is called a stopping time. So what's a stopping time? So it's a random time taking values 0, 1, 2, and possibly infinity, with the condition that tau equal to n. If I look at this event tau equal to n, this must belong to this filtration Fn. Okay. So for example, we have defined this stop time. The first time, starting from A, it is the xn Sn becomes 0. So this is essentially this event. So tau equal to n, tau a equal to n. So it is that the random walk was not equal to 0 for I equal to 1 to n minus 1, and Sn equal to a. Sn a equal to 0. So this is an event in terms of, just you see, S0a, S1a up to Sna. So this is something, a event given in terms of these random variables, and that is of course, so is something, all these things belong to a certain set H. So therefore this is in Fn. Okay. So this is the first thing. And the second point that we want to talk about is something what is called a stopped process. So I have a sequence of measurable, Fn measurable random variables xn, and tau is a stopping time. Then I want to define the stopped sequence. So what is the stopped sequence? It is denoted by xn minimum tau. So if tau is less than n, then we look at only up to tau, x tau. And if tau is bigger than n, then we would look at xn. So for example, let's say for some omega, tau omega equal to 20. So I will have x1 minimum tau would be x1, x2 minimum tau would be x2, x3 minimum tau would be x3, and so on up to x20 minimum tau would be x20. But what happens to x21 minimum tau? That would become x20, because then tau is now less than equal to n, right? Tau equal to 20 and n equal to 21. So you stop at 20. So this, and 22 minimum tau, that would also be equal to x20. 23 minimum tau, that also becomes, so from that stage onwards, you are fixed at x tau. Or in this case, fixed at x tau. Okay, so this is one of the things that. So if you want to look at the sequence of random variables up to a certain point, which is random, this is how you study this. Okay. Now, I want to. So this I will not spend time. This is it is written here over here how to prove this. This xn minimum tau is a Fn measurable. You just write down in terms of all possible values of tau what it can take up to n, and it is a tau bigger than n, and you just write down that this set is clearly, you can see tau equal to, so when let me say the second case. First case is trivial. The second case, tau bigger than n, and xn so when tau is bigger than n. Okay, so then what happens to xn minimum tau? It is equal to xn, right? So in this case, it is going to be xn. So in this h is going to be tau bigger than n and xn in h. And this thing we can write is tau less than equal to n complement intersection xn in h. This is of course in Fn, that is the Fn measurability. And this part, okay, so this part, what is the complement? So tau equal to 1, tau equal to 2, up to tau equal to n, this union complement of this. and each of this tau equal to 1 up to tau equal to n are in Fn. Their union is in Fn, so their complement is also in Fn. So this intersection is in Fn, and the same logic is here also. Okay, so this set is in Fn, therefore this is measurable. Okay, and this is the main thing that you want to remember. I want you to remember. I'll not though the proof is two line. I'm not going to the proof. So if xn is a Fn martingale and tau is a stopping time, then x n minimum tau, this should have been also 0, greater than equal to 0, is a Fn martingale. Okay, so this is the main thing that I wanted to remember. Nothing more than so. This one, the proof is very simple. You just write down possible values of tau, and then just see, use that xn is a martingale. Therefore, so this essentially you see that this set will be in Fn, and you have to use this property of the martingales. So I just this property of martingales would be required, and that would become xn minimum tau bigger than n. But other things are exactly as it is, and this would become the xn minimum tau. Okay, and this is the expectation. This is the conditional expectation. Oops, sorry. The conditional expectation definition that I have written. This is the conditional expectation definition. Okay, so the two things that you have to remember is that xn is a martingale, Fn martingale, tau is a stopping time, then xn minimum tau is a Fn martingale, and this is also n bigger than equal to 0. And the only other thing that you want to remember is this part. When if I have a martingale, the expectations remain same, constant for every n. Xn equal to expectation of x0 for every n. Okay. So these are the two things that I want you to remember. Okay, so now I go to the main definition of collision time of 3 random walks. So I have now starting with 3 random walks, starting at -2i, 0. The middle one I'm putting at 0, and the so I, j are positive. Okay, so I and j are both are positive, because that's how I want to make it. -2i, 0, and 2j. Of course, they all have to have even parity, the same parity. So starting with even parity. Okay, and so what is the collision time we are defining? So collision time is the first time one pair of them hit each other, one pair. So which is same as the product becoming 0 for the first time. So remember, the product started both of them, the distances. If you look at this is the distance between the so if I think of the left, right, and the middle, so this is the between the left and the middle. This is the right and the middle, their distance. So when one of them becomes 0, the product becomes 0. So this is the first time the product becomes 0. And the theorem that I want to present is essentially tau. The expectation of this is 4ij. This is a neat expression that you can find for this, and very surprising. And I didn't find this expression anywhere. So here it is. Okay, and so so generally it is said that you should have a joke and a proof. I do not have a joke, so instead I will give 2 proofs. Okay, so I need so why did I go through all the things about martingales? Because I am going to use martingales. Okay, so let me martingale. So I have to define a sequence of as a filtration. So if the filtration will be the random variable, the smallest sigma algebra generated by the 3 random walks. So up to time n. So at time n, whatever information that they are generating. So the smallest sigma algebra with respect to which all processes up to time n, all the random variables up to time n are measurable. And of course, this is same. So if I know the increments, I know this, and vice versa. If I know the position of the random walks, I know the increments. So so these 2 sigma algebras are the same. Okay, so I need 2 lemmas for this. I will prove the first lemma, and this is the first lemma. So this product, as I said, the distance plus n is a Fn martingale. This I am going to prove. And as you see, you will, it's a trivial proof, just elementary calculations, nothing more than that. Okay. And the second, also this is another martingale. That if you take the product of all the distances, this is also a Fn martingale. I would point out that this is a standard martingale. This is known for, this was known already. In fact, in general, if you start with k sort of random walks and you take all their products, all possible products, and that product is a martingale. Okay, but this martingale is new. I have not seen it earlier. So this is a new one that we have found, and once you find a martingale, actually things become trivial. Okay, so again, so to show martingale, what you need to show those three conditions, and the first two conditions, as I said, are trivial. By definition, and the second one follows. The first one is again maximum distance. You can just write down it is less than equal to some constant. Depending on this n. Okay. So what is the third condition that we want to verify? So we just write down the value at time n plus 1 and minus subtract the value at time n, and you see what is the thing that we get. And you want to show that actually when I take conditional expectation with respect to Fn, this part becomes 0. So it is just, I've just written down Sn plus 1 at 2j, which is Sn plus actually this increment, Sn plus this increment, and this is Sn plus 1 at 0, which is Sn and this increment. So you just write down, subtract, and you just multiply out. One things cancel, this is cancels, n and n cancels. So you would left with this 1 here, and the two cross product terms, this part, and the product of the increment terms. Okay, so this is essentially just elementary algebra, writing down this as Sn plus the increment, and this is also Sn at time Sn0 minus the increment, and the sort of take out the increments as a separate term, multiply, and you get essentially this. This is just elementary calculations. So now I have to take conditional expectation and show that this is 0. And for others, I actually would see immediately, but still, let me go over this. So let's see the first term. Okay. So we are conditioning with respect to Fn. So up to n, everything is fixed. So if I look at this first term, I want to show that this first term is has expectation 0, conditional expectation, when I fix up to terms up to n. So these two are fixed. This is some, let's say some k, and this is some l. So this is now given. Okay. So therefore, I have what is that I have to compute expectation of? I have to compute expectation of this, and this does not depend on what has happened up to n, because this up to n, those are increments up to time n, and this is increments at time n plus 1. So these are independent of the previous values. So I have just I have to just compute expectation of this. So this is taking, so this this expectation is 0 and equal to 0. This one step with respect to Fn. So therefore, what is that we get? So this is the thing that informally if we can do. Is that Sn 2j minus S2j. This will come out of the expectation. This is constant. It will come out, and the expectation is 0. Okay. Similarly, the second term is also 0. Okay. This is not, there is nothing here. So look at the third term. So if I look at the third term, now this is again independent of everything else. So it is just expectation. So when I multiply out, so this times this, if they are independent, expectation, product of expectation equal to expectation of product. So that becomes this is 0. This and this, that is 0. This times this whole square of in plus 1 0. and that takes only one value, 1 with probability 1, and therefore this expectation is 1, and minus of that, that is minus 1, and that minus 1 will actually cancel with this, and this times this also will be 0. Okay, so that is essentially the proof of the lemma. So now I come to the proof of the theorem, and I want to show the proof of the theorem. So I've just shown that this lemma, this is a martingale. So I use a stop tau collision. So a tau collision is the definition. Let me go back again. So this tau collision, this is again, clearly you can see that this is determined by the process up to time n, right? Whether tau equal to n or not, these are only random variables, that this product is not 0 up to time n minus 1, and this product is 0 up at time n, and therefore, and all of these random variables are Fn measurable. So therefore, this is an event in Fn. So this is a stop time. I have shown that this is a martingale, so I get the stop martingale. Okay, so these are, then I use the next result, which is that the expectations are 0. Expectation remain the constant. Okay, so expectation of at any n is same as the expectation when I n replaced by n by 0. And tau collision actually is greater than equal to 1, but the minimum value it can take 0. Right? So 0 minimum 0, that is always 0. So all this, so this becomes 0. This is also 0. Is S0 2j, S0 j. This one becomes S0 0, and this becomes S0 minus 2i. And this is 0. Right? 0 minimum, whatever positive that is, non-negative, that is 0. And what is this? I can write down this. This is 2j, this is 0. This is 0, and this is minus 2i. So the product becomes 4i times j. So this expectation is 4i times j. Nothing. Okay. Next, let us look at, so this I have two expectations. So expectation of this term and expectation of this. Let us look at the second one, which is easy. Now let us look at this random variable. So what happens? Okay, by the way, the tau collision, this is always finite, because we know tau coalescing time is finite, right? This we can show directly that tau collision is finite, but I don't want to go into that. Tau collision, because one of the three things, one of the two pairs will meet. That is obviously smaller than the time that the first two meet, right? And we know that the first two will meet for sure. So therefore, this is for finite almost surely. Now, so think of this situation that tau collision is finite. So it takes some value. Let's say it takes value 30. So what happens to this one? So 1 minimum 30, that is 1, 2 minimum 30, that is 2, 3 minimum 30, that is 3, and it goes up to 30 tau, which is 30, and 31 minimum tau, it remains at 30. 32 minimum tau, that remains at 30, and so on. So for every n, which after some time where this value is achieved, this is some value tau omega, and after that, this tau minimum n is at tau is equal to tau. So therefore, this, and as you see that this is increasing and increases to tau collision. Okay, so I can apply MCT here, and MCT will say expectation of this converges to MCT of tau collision. So this part I have got that this expectation converges to tau collision. Okay, so next, if I can show that this expectation limit, so I want to take limit on both sides. This side does not have n, so this side will take limit. This side, this part I have shown already expectation of tau collision. This expectation I want to somehow show that this limit will be 0. Okay, how we can do that? That is the next part. And even without doing anything, okay, so we will come back to this later. So let us see first this. Again, the tau collision, it is finite, and that will imply again the same logic that I have said here. As n is bigger than tau collision, one of this pair would become they have met, and they are fixed at that tau. So therefore, that becomes as differences become zero. So therefore, this product would become zero, and from that state onwards, this product will be zero. So this goes to zero almost surely. Now I need limit and expectation I need to interchange. Okay. So I need something to interchange. So here I have used MCT. Here I you have to use something else, and this is where the second martingale will come. Okay, so the second martingale I have already now saying that not only that this is a martingale, and therefore the tau collision part that also is a martingale. Okay, the second martingale. So again, the same expectation will remain the same. So you just look at the expectation at every stage, and that becomes the same value at expectation at time zero, which is this is 2j, this is 0, this is 0, this is minus 2i, so this becomes plus 2i, and this becomes 2i plus 2j. So the product here becomes 8ij times I plus j. Now remember, these are fixed. So for every n, this expectation for every n is equal to this value, 8ij times I plus j. Okay. And now we make the sort of one crucial observation that we are looking at this process only up to this collision time. Whatever happens after the collision, because the process is being fixed, n, if n is bigger than tau, we are taking tau, right? N is bigger than tau, we are not looking at after that. So but up to that time, the distances are always been greater than 0, and at collision time distance becomes actually one of the distance becomes 0, one of the distance. So these two are always non-negative. This is one thing that you have to have to keep in mind. Okay, so if you keep this thing understanding this, I'll just now go back to this previous page. So this is always non-negative. So this expectation this ij, and so therefore from here, without doing the other work, what you can show that expectation of tau collision is less than equal to 4ij, because this is that part is already less than equal to it is bigger than equal to 0. This I already know. So I'm taking out thing greater than. But I want to show that this precise expression. So now I will use this trivial inequality of A and GM. Square root AB is less than equal to A plus B by 2. And we have, so, so I want to use this inequality on this term. Okay. So I've taken the modulus and taken 3 by 2. So though it is sort of non-negative, just for the sake of writing, I have written modulus. So first I will remove the modulus, and then 3 by 2, one square root I'll replace by this, and the other parts will keep as it is, right? So this times square root. So this becomes so one terms I have kept as it is, and the other terms I have replaced by the sum. So what is the sum? So is the sum, these two cancels, so you get tau tau collision 2j minus s n tau 2j. So this is exactly that sum, right? And I get a half. This is a plus b by 2. So, and this expectation I know for sure it is equal to 8i this, so half of that, so 4ij into I plus j. So for every n, expectation of this thing 3 by 2 is, so is
I think he's lost his connection.
Anishda, maybe because of some link failure.
I, mm,
Hello, Anishda, are you there?
yes, I think Anishta
yeah,
is.
Yeah.
yeah.
So go ahead with this screen sharing again.
Okay, so presentation. Yeah. Okay. So can
Yeah, yeah,
okay.
yeah.
Yeah,
We can see. Yeah.
yeah, that's
Okay, so we have now given a formal proof of this thing, and what you required is only these two things about martingales, showing some two products are two terms are martingales, two sequence of random variables, and two results about martingale. One is that the expectation remains same, and the other is the stopped martingale. Stopped part is also a martingale, and so. Uh, so if there are any questions, at this point we can take that questions. Okay. Hello.
I think you can continue.
Okay. So
There's no question.
okay. So if something happens for random walks, the same things should happen for Brownian motion. And now we have you can take three Brownian motion. We start from minus x, 0, y, and you can define tau collision of Brownian motion. And in the first time one pair meet, and then you can, for that you can prove that tau collision of Brownian motion is exactly x times y. Okay, so exactly the same martingales, except that it would be replaced by the continuous time versions. And there is an extension which actually we worked on this extension, and then we came back to see that this for random walk it gives a exact result, uh, and so on. So, so this is saying that if I have a FN adapted process and taking values on a countable set, and if I have a hitting M, which is a subset of this M, and then you are looking at the first entrance time from anywhere. So M is a set here. So that's why it is used, the terminology is used in entrance time. So the first time you xn enters M, and then if we have a condition like this, that the process, there is a b which is greater than equal to 1, and a p naught which is positive, such that the when I take the v is a non-negative function of the state space. The state space is M to 0 infinity. So this function in the increment of this v is bounded by minus 1 plus b times indicator xn is in m0 to m1, m0 or m1. So m1 is another set. So in our case, if you vf this v function, it is the product of the distance. Okay, and this set m1 does not exist. This is empty set. But in more sort of general dependence cases, there will be this kind of exact expression of that everywhere it is equal to minus one or some or condition, that is unlikely to happen. So what is, there will be some dependence, and there may be sort of this is saying that when I take look at this function v of xn, it is sort of attracting. So every time you are sort of doing, you are reducing. But when the functions, the sorry, the the random variables are in certain sets, this may not happen. So that is what we are sort of saying, okay, this on this set is not going to happen. Not going to happen. Okay, but we are saying that whenever you are in this set, you hit the set that you want to m naught, that probability is bounded by a p naught, and then for every x in m naught, the v of x is the starting point of where you started your process. This should have been xn. Everything I've this is an x naught, not y naught. It should be x naught. Okay. Okay. So now I will go to the directed random tree and the Brownian weight part, and this will do essentially do with pictures. So we start with a random. We start with a lattice and oriented lattice, what is always called Z2 even. So x and t are such that, so this is that x plus t is here. So think of this 0, 0, then this is 2, 0, this is 4, 0, and this is 1, 1, 1, and this is minus 1, minus 1, 1, and so on. Okay, so you are removing some of the points, oriented lattice. Okay, now we want to define a sort of random walks on this in a certain way. So for each vertex, you will go to either or northeast direction or northwest direction with probability half. Okay, and then keep on doing the same thing from there. So here I am taking the time going up in this direction, and if you just let me just one more. So if from here I have gone to the north, gone to the right, then to the left. So this has success. So success goes right. This is here I get a failure, so get left. Here I get a failure, I go left, and here I get a failure, and then here I get a success, and go on like this. And I do it from every point. So you get a picture like this. Okay, and now let us look at one of these. Let's say I start from here. So you see that if I look at the time in this direction, so at time +1, so time in, so you go to +1 or -1 with probability half each. And there from here also I go to +1 or -1 with half each. So if you look at follow this path, follow this path, this is going to be a random walk. So each of them, and you follow each of them, this is a random walk. You just again the same logic. And these two paths, so if I look at this path and this path, let us look this two path and this path. So this is, once they have gone together, then they are here, they are using the point tosses of this point, and therefore it is going to the same place. So they are going, that's what we want to say, coalescing random walk. They are going together. Okay, and from here, what until they coalesce, what happens? So this one uses the coin toss of this point and this point up to this. This one uses coin toss of this point and this point, and all the points, so they evolve independently of each other until they meet, because they are using the coin tosses of independent coin tosses. So this paths, this is a collection of paths. Now instead of one, I have now countable number of random walks starting from different time points, and once they meet, they sort of go together. Okay, so this is a particular model of, there are a lot of things we could say about this, but I'm not going to go into this. I want to give another example, and this is something called the drainage network example. This is a Howard's model, and we introduced this model in the sort of probabilistic framework. This is Gangupadhyay, Roy Sarkar in 3. So here, this is a part of the Z2 lattice. There are all points up there, and I toss coin independent coins for each point to have the keep certain points only. So in the network sense, these are called essentially source of water. But anyway, so let's not get into these things. And so how they connect? So the rule is to connect to the next level as we had done in the previous the next level in a sort of locally defined rules. So how it is done? It is that so every point from here it chooses in the next level which is the closest point. So for example, this one it chooses the closest point is this, and it will connect. Okay, and then from there it would sort of continue. But now I see that here there are 2 points which are closest, this one and this one. So in this case of a tie, we will break the tie with probability half. With probability half, one of them I will choose. So and then you keep on doing this. So I will get a path like this. And again, if you look at this, if you look at this path, so this is a random walk essentially, not now anymore or just taking plus minus one values, but the values are in Z. This if this point is open, I have to connect here. Okay, and the probability of connecting here is the same as the probability of connecting here. So and so on. Okay, and you can write down this exactly. This is a symmetric random. Now I would do it with all the points, and you get a picture like this. This is all essentially all the points you have done, and this is I will talk about this a little bit more, maybe in a couple of minutes. So now next thing is a continuous time model. I don't want to go into this. If I have time, I don't have time so I'll not go into this. Now, and quickly I want to sort of introduce one more object, which is the Brownian wave. And I do not want to sort of do any formal things. Just look at this theorem, which is the most important part. So it's a random object. It's a random collection of paths. Random collection of paths. So that is the some state space you can define, where you have a few things about it. So for every x in R2, there's a unique path pi x in this collection. So for every point, there is a path pi x. Okay, and if you take finitely many points, so these are deterministic points. So there are of course now for if one there are of course these are all almost sure statements. I should have said they're almost surely. So almost surely there are pi x1, pi x1, pi x2, pi xk many paths from each of them from this k, and their distribution is a coalescing Brownian motion starting from x1, x2, xk. And the third one of the important property is that if I start with any countable dense set D, then if I look at the collection of paths, so this is again is some subset in some space, and if you take so there is a topology in that, you take a closure on this that determines this path, determines this random object uniquely. So any two sort of collection, any two collection that would give you the same thing. That is what it means. Anyway, so the main thing is there is an object like this, which we do not want to go into the details. But why we are introducing this is okay. So that many of them, the models that we have defined, actually the two models that I have defined and another one which I did not, they converge to this Brownian wave. And for that, I would want to introduce just one notion of a random variable. So take, consider this. This is the path count of paths, count of distinct paths. So I have A and B on this point. This should have been T naught, and I have a going to the height t. So this length distance, this height is t. So this should have been t naught plus t. I don't know why it has come something like tt and t, something like that. And I am looking at this on that line t naught 2 points. So a, so these two are actually a t naught and b t naught. And we are looking at all paths which start before time t naught. So, and it goes through this a to b, goes within this line segment, and has distinct points here. So number of distinct paths of starting inside A to B. So, so for example, if I look at this one, this is one distinct point, and this is another distinct point. So two of them, though this two started, but here I ended up with one. So I count this. This has two. This is not counting because it is not started before t. And if I started before t, something may have gone from here. That also is not counted. Okay. So in this case, this should have is equal to this count of paths is equal to 2. Okay. So this random variable is a important random variable, as the conditions is saying. So one of the conditions is saying that, so I have some sequence of non-crossing paths. Non-crossing paths means that paths cannot cross without coalescing. And then so this is a kind of finite dimensional distribution kind of thing, that if you have x1, x2, xk fixed finitely in points, and then in the limiting xn countable the sequence limiting, there are paths x n pi 1 pi n x1 pi n xk, they will converge in distribution to coalescing Brownian motion starting from x1, x2, xk. This is of course have to have. And the other two conditions, one is saying that when this length, so this is a, and if I take a plus epsilon, and this can be t and this can be t naught. So when this length is epsilon, and epsilon I am going to let go to 0. So the number of paths is greater at least 2, that is going to 0. The lim sup of this probability is going to 0 as epsilon goes to 0. And the number of third condition, number of paths is bigger than equal to 3. That part divided by epsilon, epsilon going to 1 by epsilon, that part is going to 0 as epsilon goes to 0. So these two conditions, B1 and B2. So this is fairly easy to verify, and in fact there are now many of these things. There are a lot of results now. Kumarjit has also done a lot of work on this, and this part also is fairly easy. It is this part, the third condition, which is very difficult in general. For even for the most simple case of the where coalescing random independent random works, this required something like a FKG inequality, and in general FKG inequalities are very tough. Okay. So now, what do I mean by scaling limits? So I take a model such as those two I have defined. So this is essentially saying that I scale the time by n square, and the space by n. So generally this diffusive scaling, I have to the space scaling should be
Anishta, sorry to interrupt, but we are already over time. So if you'd quickly wrap up, that would be nice. Thanks.
Okay. So the diffusive scaling, and you would require this to this thing will converge to. So if you take a collection of paths like this, and this would converge to Brownian motion. And the known results are, of course, all these things, all these models that I have defined, these are known that they converge to this. And so I couldn't come to this collision time business, but the thing that just let me go to this one last part. verification of B2. So this was the verification of B2, uh, where the verification of B2. So let me spend a couple of minutes on this and just, so it just, the first thing was A and T naught, and these models are translation invariant, so there is no difficulty in setting one of them to be zeros, A to be zero and A and T naught to be zero. So you will just make this A to be 0 and T naught to be 0, and all the probabilities remain the same. So you have something like this that you want to consider. And the result that we have stated, that the result is proven, can be proved, that the collision time of, if we start from 3 random walks, which is starting from 3 paths. So instead of random walks, now we should say paths, I0, J0 and K0. Their collision time, we can show that this is less than equal to exactly a similar kind of thing. This is C1 times C2. So the random walk case, the C1 was not there, and there is this part was only constant times like this, and exactly a constant value was known. But here in this case, we get a upper bound like this, and just I will just explain this one last argument, is that if you think of this 3 paths thing, so so the paths we had something like this, that there are 3 paths here in this scale. So that would mean that if you start from the, look at the path from the left, from the origin, and then I look at the next path from the origin, and the next one, until I get a situation that this path and this path I do not coalesce. So that is the first thing that I would say, that there exists a I such that the blue path and the I plus 1, that the red path, do not coalesce. Okay, and there has to be 3 paths. So that will mean that there another path which is from to the right of the red path, this is a magenta path, that would not coalesce. And if the magenta path is there, non-crossing property would say, okay, if I look at from the root n, the n epsilon point, that should be to the right of this path. So that means I get this green path, which would be the right. This might have coalesced with this one. But if there are 3 distinct paths, I will get a I such that I does not, the path from I0 do not meet path from I plus 1, 0, and the path from n epsilon 0 also do not meet any. So this is the last essentially slide. So you get that at least 3 events is contained in this union I equal to 0 to n epsilon minus 2, that the collision time is I starting from paths I plus 1 and n epsilon bigger than n squared t. And now you just use that this union is less than equal to sum, and then use Chebyshev inequality, that is less than expectation of this by this, and then the very rough estimate n squared t is a constant, comes out c times the total number of sums, which is at most n epsilon, and this is less than n epsilon. So that C2 times n epsilon I take out, and the total number of terms is n epsilon, so that is n epsilon. So I take limit as n first lim sup of n goes to infinity. So this part would get cancelled, and this part would just give you c squared times epsilon by t. And now I have to divide by epsilon, take limit epsilon goes to 0, and that, of course, one epsilon is left, and that will go to 0. Okay, so this is the sort of application that you have, and otherwise this part is, this is a very, from this there is no easy way of estimating this. It requires a lot of effort, and in both papers this is a significant portion, 7-8 pages of technique that has to be developed for this, whereas this gives a very robust estimate for many cases that it can be applied to. Okay, so these are the continuous time things which I have not go into. So I will stop here. Thank you.
Thank you. I request everyone to unmute and give a loud applause to this wonderful talk. We are slightly over time, but we can still have few questions. If you have a question, you please unmute yourself and ask.
Anish,
Yeah.
I'm Rahul.
Yeah.
Can I ask?
Yes, yes, please go ahead.
What happens if you have crossing paths? Will can you because then the conditions are different? Can you get something?
So let me do a propaganda here. So I think at least for the case where the increments are bounded, we should be able to do it. And it may not be a sort of sufficiently sort of a project, but we can. So I want to do this project if there are many, I think, MSTAT students who are looking for projects. If they're interested, we can study this. I think it should be possible to do it as a MSTAT project, at least for the bounded increment case.
Thank you.
And of course there are, in this case there are actually many things, small things are there which we can also, and also there are many hard things are there. We didn't talk about Brownian net and crossing path convergence and many things are there, so which are for thesis, but for there are many small things which are there which can be studied as a MSTAT project also. That's what I wanted to sort of give a propaganda about. Okay, so if the students are interested, they can contact me.
A question which came in my mind while listening to the first part of your talk. So the classical result says that if you have a simple symmetric random walk, then and you put two barriers, say one at I and one at, or in your way, one at J and one at minus, or one at 2J and one at minus 2I, then the hitting time expectation you will be 4ij, right? So
Yes.
what you are having is that you are having two random walks further. They are not constant barriers, right? So there is a straight, the answer is same. So there must be some universality that what kind of barrier you are looking at?
There may be, yeah. So in this case, we have not, we just studied it last year. So we,
Okay, okay.
which are open here,
Thanks.
which we can do.
Any other question from anyone in the audience? If not, then let us thank Anish Sarkar once more. Thank you.
Okay.
So let's close the session.